Collisions and conservation laws. Okay, these were our discussion questions for today in class. What happened to momentum in collisions? What happened to energy in collisions? If it wasn't the same in all of the collisions, what happened to the energy? And can we categorize collisions by what happens to the momentum and the energy in them? So, after you guys had a conversation, we talked about conservation laws. It's very important to remember that conservation laws apply in a closed system, so when there's no external interactions. We will always include collisions as a closed system, but those aren't the only times that conservation laws apply. So, momentum is always conserved in a closed system. The total amount of energy is conserved, not necessarily any individual kind of energy, but total energy is conserved. Mass is conserved, and electric charge is conserved. Now, we aren't going to deal too much with the third and fourth ones there, mass and electric charge, in this unit, okay? If you go into further physics, you might deal with the conversion of mass into energy, but for AP Physics 1, mass is conserved. Electric charge is conserved, but we're going to deal with that later on in our other units. Okay, in a collision specifically, momentum is always conserved. This is why you are always use conservation of momentum to solve a problem dealing with a collision. Unless we have certain circumstances, you won't be able to use energy, because kinetic energy is not always conserved. Total energy is always conserved because we can count the collision as a closed system, but sometimes we're going to lose that kinetic energy to things that we can't really quantify without more information. So, the types of collisions. If kinetic energy is conserved, we call it an elastic collision. This was when your setting on the simulation was 100% elastic. Okay? In real life, yeah, that doesn't really happen, but in physics world, it does. So, if kinetic energy is not conserved, you get inelastic collisions. A subset of inelastic collisions is perfectly inelastic collisions. This was the special case where your elasticity setting was set to 0. So that means there was absolutely no bounce afterwards, so the objects stuck together after the collision. Now that was a lot of words, so let's put this in pictures. If it's a closed system, momentum is conserved. There can be other interactions in a closed system that aren't collisions. So, if it's a collision in a closed system, and kinetic energy is conserved, it's elastic. So, this is a subset of interactions in a closed system. You'll notice that this oval, does not overlap, It's either elastic or it's inelastic. You cannot have a collision be both, okay? In an inelastic collision, kinetic energy is not conserved, but total energy is. Okay? Because you'll notice it's still within this closed system, so total energy must still be conserved. And then there's a subset of that, perfectly inelastic collisions, where the objects stick together. You notice that this rectangle is completely within the green oval, therefore it follows the same rules about total energy conservation, but not kinetic energy conservation. So, where does the kinetic energy go if it's not conserved? Well, you have to deform the object as it collides. And then, based on the elasticity of the object, it's either really easy or really hard to go back to its original shape. So, if it's 100% elastic, it goes back and you don't lose any energy in that process. But, if it's 0% elastic, that's when you get them stick together. In the middle, when you have a collision, you're going to hear the sound. You'll also actually lose some of your kinetic energy in the form of heat, although that's a lot harder to actually put your hands on and see, or hear. Alright, so we have to talk about this change in energy. And when we studied position, change in position had a special name, displacement. And we studied momentum, change in momentum has a special name, impulse. Turns out, change in energy also has a name. So if energy is gained or lost by a system, or even by an object, we have a special name for it, work. The equation is work equals the change in energy. Now, if you go look at your AP equation sheet, there's more after that, and we'll get to that when we deal with forces. For now, all you have to know is work is the change in energy. So remember that delta means final minus initial. So this is why my energy value in AP Physics 1 can't be negative, but the change in energy can be. If my final energy is lower than my initial energy, my work will be negative. Okay, and then here's the semantics. If work is done on a system, it increases the total energy in that system. So that means the value for my work will be positive because final is greater than initial energy. If the system does work, then we say it's work done by a system, and it decreases the total energy in that system, giving me a negative value for work. We're going to talk more about total energy and work and how energy transforms in the next couple of lessons. The key points for today, we're talking about conservation laws, when they apply and what's conserved, types of collisions, and the fact that work is change in energy. Your homework, don't forget projects are due tomorrow and the mastery quizzes close Friday. And for your exit ticket, does a system gain or lose energy during an inelastic collision? Well, trick question, right? A system won't gain or lose energy, it stays constant. However, it does lose kinetic energy in an inelastic collision. So if you're going to talk about the work, right, to keep track of the energy, in this case the work's actually going to be negative, okay, because your final kinetic energy is lower than your initial kinetic energy. So the work done has to be negative, okay? And then if the work is negative, it is work done by the system.